Transmission X-ray microscopy has become a powerful technique applied in various scientific fields, including materials science, environmental science, and cell biology. In the post-Moore era of the semiconductor industry, advanced packaging has become increasingly critical for meeting the demands of high-performance microelectronic products. There is a growing need for non-destructive imaging of submicrometer structures and defects. Micro-X-ray computed tomography has been proven to be a powerful tool for non-destructive three-dimensional imaging of voids and defects. However, increasingly smaller feature sizes in advanced packaging and the need to detect smaller defects require X-ray imaging solutions with a higher spatial resolution, that is, nano-X-ray computed tomography in a lens-based X-ray microscope. Transmission X-ray microscopy setup. A transmission X-ray microscopy setup consists of an X-ray source with condenser focusing optics, objective lens, and a detector. The specimen observed is then placed at the point where the beam focuses. Laboratory X-ray microscopes usually use solid or rotating anode X-ray sources using chromium K-alpha or copper K-alpha radiation, a glass capillary as the condenser optics, and a Fresnel zone plate as the objective lens. In order to increase the number of photons generated at the source, the latest developments rely on liquid metal jet X-ray sources, which allow researchers to increase the photon density. Solution for deep object penetration, X-ray source and optics combination. For photon energies higher than 10 keV, the efficiency of FCPs drops significantly. The limiting factor is the height of these zones, since the aspect ratio is limited using conventional patterning techniques for FCP fabrication. To overcome this limitation, in our development of a system with a liquid metal jet X-ray source using gallium-indium target, a side-by-side Montel multilayer X-ray mirror was used as the condenser. The optic was designed for a 24 keV indium K-alpha radiation, and its geometry allowed us to reach a beam size of 80 micrometers at full width, half of the maximum at the focal point. Next, as the objective lens, we used a multilayer Laue lens, a diffractive lens consisting of two focusing multilayer stacks. These are thick enough to preserve diffraction effectiveness also for high-energy photons. Siemens star test pattern images. The imaging performance of the described X-ray microscopy setup was demonstrated using an X-ray resolution target that included a Siemens star test pattern with a minimal feature size of 150 nanometers, patterned into a 1500 nanometers thick tungsten absorber. Features lower than 150 nanometers were resolved. The setup with the described combination of a Montel mirror and a multilayer Laue lens allows for tuning the magnification by changing the multilayer Laue lenses to detector's distance. Application in microelectronics, solid-liquid interdiffusion bonding. The transmission X-ray microscope previously described was applied to the non-destructive imaging of buried metal structures fabricated using advanced packaging technologies for the 3D stacking of silicon dies using copper stannum solid-liquid interdiffusion bonding. A 3D scheme of an investigated SLID structure is presented in the bottom right to visualize our sample array, which consisted of 2 microbumps. SLID sample. Demonstration of deep object penetration. We imaged a SLID bonded sample after placing it in the beam without and with an additional blank piece of silicon wafer with a thickness of 680 microns. This additional absorber caused only a 25% loss of X-ray intensity and caused some darkening in the image. Next, we rotated the sample by 90 degrees to visualize the SLID bonding. We have shown that the combination of 2 multilayer optics in a laboratory transmission X-ray microscope allows for the high-resolution imaging of objects in the hard X-ray regime. Using 24.2 keV photons of a liquid metal jet X-ray source with a gallium-indium target, the penetration depth of the X-rays into the materials was significantly larger compared to the 8 keV photons used in state-of-the-art laboratory transmission X-ray microscopes.